Today we're going to be working through Maclaurin Olympiad 2023 questions 6. Let m and n be fixed positive integers. Prove that there are infinitely many triples of positive integers x, y, z such that x to the power of mn plus 1 is equal to y to the m plus z to the n for each pair of values m and n. So at first this might seem a bit intimidating because there are 5 unknown variables, but we can try testing some small cases. So I'm going to do m equals 2 and n equals 3. And if you substitute these into this equation here, we get this equation. So x to the 7 is equal to y squared plus z cubed. So our challenge here is to combine this addition term into a single power. Now the key idea that's going to allow us to do this is by using powers of 2. If we have 2 raised to a power and we add that twice, we can factorize a 2 out and write it as a single exponent of 2, as shown here. So if I let x to equal 2, then we get 2 to the 7 is equal to y squared plus z cubed. Now we just have to make y squared equal to z cubed. Do this by setting our y squared equal to z cubed. And we know that they both have to be a power of 2 because of this. Now, if I set y to be 2 raised to the 3 and z to be 2 squared, we can see that we basically use the other one's exponent. So y has a square here, but we're using cubed in our substitution. And z has a cube here, and we're using a square in our substitution. And once we plug these back into our equation, they cancel out nicely to get the same number because they multiply. Now luckily 2 to the 6 plus 2 to the 6 automatically equals 7, so we can get a valid solution. Now that we found a working small case and we've spotted the pattern of setting the exponent to the other one's exponent, we can generalize this for any n and m. So to do this, I'm going to set y raised to kn and z raised to km. And you can notice that the m and n are swapped again, as said before. But I've also used k, which is a parameter, and this creates infinite solutions for our equation, because that's what the question wants us to find, not just one valid solution for n and m. Now, if you substitute this back into our equation, the right-hand side, which is this bit, will collapse into 2 raised to the knm plus 1, as shown through this algebra here. I can also generalize the left-hand side now, as I know x to the nm plus 1 is equal to 2 to the knm plus 1. Since x is an integer, I know that the left-hand side's base has to be 2. So I let x be 2 to the a, but I don't just use 2 because if you look at the right-hand side, k is a parameter, so we can change that to whatever we want. So this 2 will be raised to any number. So we need a parameter on the left-hand side to change accordingly to maintain this equality. So now if I substitute this back in, I get this. I can reduce the bases because they're both 2, and I get a multiplied by nm plus 1 is equal to k nm plus 1. We now need to express these two parameters a and k using one independent parametric variable, and I'm going to call this p. So we're basically finding the connection between a and k. To introduce this p parameter, we have to find the relationship between a and k from this equation. To do this, let's make the algebra a bit simple by letting f be nm plus 1. Now if I substitute this back into our equation and do some manipulation, I get f times a minus k equals 1 minus k. I notice that this is a nice multiplication, so I'm going to take the mod of this base f. So this f is equal to 0 mod f, so this left-hand side just cancels down to 0. and I get that k is congruent to 1 mod f. Now I can write this algebraically by saying k equals pf plus 1. And p is the variable that acts as the seed that can generate our infinite solutions. We need to now figure out what k and a are in terms of p. For k, this is quite simple, as we just have to substitute f back into this equation, and we get k equals nmp plus p plus 1. For a, we just need to do some more algebra. So recall that AF equals this and K is this, as we've just derived. If I substitute K into this equation here and I expand it, I get this equation that at first looks like a quadratic. But since N and M are positive, as stated in the question, and F is more than 0 because of this, we can simply just divide everything by F. And once we divide everything by f, we can also substitute f back into it, and we get this equation here. And if you expand this, we get a equals nmp plus 1. I appreciate that we've done a lot of definitions and derivations, so let's just collect our thoughts here. So first, we set y to be 2 to the kn and z to be 2 to the km. We switched around the n and m from the original equations, so they multiply out to make the same number, and this gives us a way to combine the two additions into a single power of 2. And for the left hand side to match this, we let x be 2 to the a, and we use this a variable to adjust and maintain equality. Next, we found the relation k has with p, and we found the relation a has with b, effectively combining our parameters into one single one that we can change easier. Now with all this information, we can create a generator function that will guarantee a triplet x, y, z for any n and m. So we need to now substitute a and k back into these and define our generator. So once we substitute that, we get these expressions for x, y, and z. Now we need to actually formalize our generator function. So let's first define the domain and range of this. So it'll take in an integer that's 0 or more, which is p, and it'll output a triple of x, y, and z that are all positive, so greater than 0. And as shown from the previous slide, I can just write these expressions as a triple and define our function as that, and just specify that p is a non-negative integer. So this is our generator function, and it will generate infinitely many triples for any integer n and m. Let's just complete this solution by verifying that this actually works, and we need to do this by substituting these values as x, y, and z. So let's do that now. So our x term will just be the first item of this triple, so that's gp1, and I'm raising that to mn plus 1 as shown here. And once I expand these brackets, I get this long ugly exponent. Now our y term is just going to be the second item of the triple, and if I expand that, I get this. And our z term is quite similar to our y term, but instead of using m as our exponent here, we use n, and we get this. Now there's some really important patterns we can spot here. We notice that the y term and the z term are equal once expanded. This is back to the idea of 2 equal powers of 2 adding to make another power of 2. And we also notice that our x term is simply 1 more in the exponent than our y and z. And we can use these facts to show that they're equal, because if our y term and z term are equal, it'll just be 2 lots of our y term, and this will add up in the exponent to get 1 more than this, which is equal to our x term. So this equality is true for any value, thus concluding our proof. Thank you for listening.